This is the 10th lecture of the first module. We will be discussing today recurrent network, the second part. Subjects to be covered in this section would be, we will revisit backpropagation through time algorithm that we discussed in the last class. Then we will introduce a real time recurrent learning algorithm. The previous algorithm that we introduced in the last class was offline, and this is online. So this was offline in the sense that we collect the data a priori from a system and then model the system, whereas we collect the data online from the system. That is, as we collect the data, we learn the model of the system. Then we will see an example of system identification using RTRL, and we will compare with the previous result, that is backpropagation, simple backpropagation through time, and RTRL. Okay, so review, as I said you, recurrent network means you have all these feedbacks. Okay, that is this is your individual neurons, and neuron output goes as feedback to all these as a feedback when they become input to the neuron. So this is a feedback connection. This is means each neuron is connected. When all the neuronal responses are fed back to the input. So this is called fully connected recurrent network. Similarly, here also there is almost same structure. If you look at this, the difference between this and this is that we have a self feedback here. That means I take from here and put it here, but in this case I don't use the self feedback. This one goes only to this neuron and this neuron. So this is a fully recurrent network. Both are, but this is with self feedback, this is without self feedback. That is, each neuron is connected to each other in feedback. Okay, so we discussed also what is feed forward versus recurrent network. So if you look at a feed forward network, let us say a discrete dynamic, a mathematical form of a dynamic is yt is a function of yt minus 1, and f is a nonlinear function, and g is g of yt minus 1. This is another nonlinear function of yt minus 1 into ut minus 1. This is a specific type of nonlinear dynamics. Obviously yt is a function of yt minus 1 as well as ut minus 1. In a feed forward network, if I model this dynamic, how do I do it? So I have a feed forward network. This can be this feed forward network can be a backpropagation network, a radial basis function network, and the output is computed while inputs are the previous output of the system, actual output of the system, and the input to the system, that is ut minus 1, and this is system output, not the network output. So this is system output at instant t minus 1. So from the system I take the input, give to the network, from the system I take the output which is yt minus 1, and what is the input to the system, which is ut minus 1. Based on that I predict what is system output to be at t. So this is the predictive model using feed forward network for this type of dynamics. But if I want to capture this dynamic using a recurrent network, the structure is that I only give input and I see what is yt. So, what you see that this particular network has no memory, hence this is a static network, whereas this has internal memory. So, this is very much like a dynamic system. A dynamic system, we give input and see the output, and a system is dynamic when it has internal memory. So, a recurrent network is more like a dynamic system, whereas a feed-forward network is a static network, simply constructed for a function approximation. The BPTT example that we discussed last time, we also considered this particular example. So, we have two neurons connected to each other. This is the connection from first neuron to second neuron, this is connection from second neuron to first neuron with self feedback W11, W22. So, if you look at this particular thing, we discussed also last time that the output, the response x1 t plus 1. So, this t is not time, t plus 1 is time step, this is time step. T is a numerical integer, okay. So, t is 0, 1, 2, 3, 4, 5 like that. So, this is time step. So, x1 t plus 1, meaning discrete dynamics we do not represent t in terms of absolute time, it is in terms of time step. So, x1 t plus 1 is f of a function of w1 I xit. You can easily see x1 t plus 1, x1 t plus 1 here is a function of w1 2 into x2 t plus and w11 into x1 t, okay. So, w11 x1 t, w12 x2 t and a function. So, normally we use a sigmoidal activation function. So, f is sigmoidal activation function. So, here it is, sigmoidal activation function. So, similarly x2 t plus 1 is a function of, now in this case x2 t, w21 and w22. So, w21 is multiplied with the corresponding input signal x1 t and w22 is multiplied corresponding input signal x2 t, okay. And this is our forward response of the network. So, if you look at now, I put this previous one, you see that I can put in this recursion. What is the meaning of recursion? I put t equal to 0, so x1 1 in terms of 0, x1 2 in terms of 1, x2 similarly x1 3 in terms of 2. So, this is a recursion relation. So, this is a recursion relation, recursive. And similarly, so what I am trying to do is that we represent the response of the network at a specific time, say t equal to 1 in terms of t equal to 0. Similarly, response at t equal to 2 in terms of t equal to 1, and we unfold the network until according to the application, okay. So, n plus 1 time step we go and expand the network. So, what is the objective here is that we convert a feedback network to forward network, feed forward network, a feedback network to feed forward network. So, unfolding network means convert a feedback network to feed forward. A feedback network to feed forward network, that is the objective of a unfolding. And then we define as usual a cost function, which is the instantaneous error at individual node and sum over all the nodes, and also then over time steps. So, as you see that our cost function in this particular case is a kind of a batch update cost function, because the back propagation through time is a offline technique. That is, I give to the system a input, a sequence of input. So, if this is my system, so I give a sequence of input, that is U0, U1 and so on, and then I observe sequence of output Y1, Y2 and so on, okay, and I collect those data, and over the total batch, for example, I have 200 sequence of input. So, we have 200 sequence of input output data. So, over those data pair we define the cost function. So, this is kind of batch, I would not say batch update, but it can be likened to batch update, because that is how the back propagation through network works. And we saw that how after it becomes a, you convert a feedback network to feed forward network, you simply apply the back propagation generalized delta rule. So, if I applying generalized delta rule, we found that this is generalized delta rule. So, applying generalized delta rule, so that is what I do. So, I find out what is error here, I back propagate this error to this and update these weights. When I found out what should be the delta W in this layer, and then the error back propagated through this weight is added with the error at the instant n at both the node, and then again the combined error is back propagated, and like that until I reach the last layer here. So, that is what we do in back propagation through time, and that is what you are seeing here. Error computed from the from one layer, it is back propagated to the preceding layer. So, this is nth layer. So, from nth layer we go to n minus 1 layer, and then we go subsequently until we find what delta W at every layer, and then we sum all these delta W's and then update the weight like batch update. This we have already discussed. So, today we will discuss real time recurrent learning. So, what is the difference real time recurrent learning? Because it is real time, that means I do not have to collect data over time from the system and then learn the model. No, I learn the model as and when the data comes, and most of our control problems, they must be dealt online. So, in that sense real time recurrent learning has a better utility than back propagation through time. As usual, as I already said, in back propagation through time, the network is rolled over in time to construct a feed forward network. Generalized delta rule is applied to update the weights. That is what we discussed just now. In contrast, RTRL, real time recurrent learning, the gradient information at t is forward propagated. So, that is I do not construct a feed forward network, rather at tth instant whatever the gradient information I have, I forward propagate that gradient instant, a gradient information to t plus 1 time step t plus 1, and gradient information at t plus 1 is forward propagated to compute gradient information at t plus 2 and so forth. So, this is the difference. So, the gradient information in back propagation through time is backward propagated through time, whereas gradient information in case of RTRL is forward propagated in time. This is a major difference. And of course, RTRL is real time or online technique, this is offline technique. Okay. Now we will take a very simple example, as we also took a simple example for back propagation through time. So, we have a single neuron, I have input xt, output is yt plus 1, we have two weights w and g, and this is a unit delay. The input to this neuron is this one, this is the input to the neuron. So, that is w xt, which is input, plus g yt, yt is the previous output. So, that means this network has a internal memory, one state memory. So, st plus 1 is w xt plus g yt, and then this neuron is a nonlinear, has a nonlinear activation function. So, output of the neuron, which is yt plus 1, is a function of st plus 1, where fh is the sigmoidal activation function. So, this was a normal structure or normal way to compute the response of a recurrent network that we have already seen. So, now you see that we will not compute a cost function like batch update we do in back propagation network or back propagation through time. This is instantaneous. So, this is instantaneous. So, the cost function is simply a quadratic function of instantaneous error, that is ydt plus 1 minus yt plus 1. This is desired and this is our the actual output of the network, and square half. So, in this network that we showed, we have only two weight w and g. So, using gradient descent algorithm, how do we write this weight? Is wt plus 1 equal to wt eta del E t plus 1 upon del w. You see that in simple back propagation network, we did not put t plus 1 as error. Error is not a function of t plus 1, but in recurrent network there are function of the time step. Why? Because it has internal memory. So, that is why these are dynamic network. Similarly, we never gt plus 1 is gt eta del E t plus 1 upon del g. So, the problem here is that for a recurrent network, how do we compute the gradient, the error function with respect to weight? So, that is what we will see now. So, if you differentiate E with respect to W, you have as usual w dt plus 1 minus yt plus 1, y dt plus 1 minus yt plus 1, and minus sign will come because this you differentiate again yt plus 1 with respect to w. So, there is a minus sign. So, this minus comes due to that. So, just for those who did not remember what we are meaning of d, E is simply half of y dt plus 1 minus yt plus 1 whole square. So, if you differentiate E with respect to w, so you have this term coming out, and then you differentiate this term with respect to w, so minus comes out there. So, now we will define a two term, which is actually a gradient term. So, pwt plus 1 is gradient term at t plus 1, and this term is defined as del yt plus 1, not del E. Please note, we are not defining as del E, but it is del y, the response of the unit or neuron. So, del yt plus 1 upon del w, okay, the partial derivative. Similarly, the pg t plus 1, g is another weight. So, if I differentiate y t plus 1 with respect to del g, then it is Pg. With the assumption that Pw0 is 0. What is Pw0? Pw0 is del y0 upon del w. Similarly, Pg0 is del y0 upon del g. So, the partial derivative at time instant 0, that initial condition, is 0. The objective is to derive a recursive relation between Pwt plus 1 and Pwt Pgt. Similarly, Pgt plus 1 in terms of Pwt Pgt. So, this is what is the theme of recurrent real time recurrent learning RTL. That is, I want to find a relationship Pt1 in terms of Pwt and Pgt. So, I have two gradient terms. So, you must know that if I have n weights, okay, and one output, okay, so then the gradient number of the gradient term at every instant should be n. More number of responses, based on that we will have more gradient information at every time, that I will discuss. But in this case, if you look at here, I have only one output and two weights and only one neuron, it has only one response. So, obviously at every instant the number of gradient term will be 2. Okay. So, that is what we will do now. We will relate Pwt plus 1, the gradient term we will try to compute at t plus 1 based on the gradient term in the previous instant at t. So, let us now compute. This is Pw, this is I can write here, this is actually Pwt plus 1 by definition. So, Pwt plus 1, which is this particular term, is y, I can differentiate y with respect to st plus 1, because yt plus 1 is f of st plus 1, and then del st plus 1 upon del w. Since yt is a sigmoidal activation function of its input st plus 1, obviously we know this particular term, that this is simply yt plus 1 into 1 minus yt plus 1 due to sigmoidal activation function. You can verify that. When this is the structure, you differentiate this with respect to st plus 1, then you will have this particular term. Similarly, del st plus 1 del w. So, st plus 1 is this one. So, this is st plus 1. So, st plus 1 is wxt plus gyt, and I have to differentiate this with respect to w. So, by definition, when I differentiate this particular term with respect to w, I get first xt, and because xt is an input, I can't differentiate input with respect to w, because input is not a function of w, output is a function of w, or response, any neuronal response is a function of input. Try to remember this, xt is not a function of w. So, hence when I differentiate this term, I only get xt with respect to w. Similarly, gyt, g is a simply weight, it is not a function of w. So, simply it is g del yt upon del w by differentiating this, and by definition this is first term is xt plus g, and by definition this one is Pwt, the gradient information at time t, okay, one of the gradient information. Okay. So, then what you get, Pwt plus 1 is finally yt plus 1 into 1 minus y t plus 1 into x t plus g p w t. Okay. So, what you are seeing is that p w t plus 1 is written in terms of p w t. So, a gradient information at t plus 1 is a function of a gradient information p w t. So, if I have a gradient information at t, I can easily compute gradient information at p w t plus 1, t plus 1. If I know the gradient information at t, then I can compute what is the gradient information at t plus 1. So, this is the basic theme of real time recurrent network. Once you understand this, any complex network you can derive. So, this is what we derived. So, similarly you can see that the other one is also in the same way, which is this one in this side. This is p g t plus 1, and this one is actually p w t plus 1. So, p w t plus 1 is a function of p w t, and p g t plus 1 is a function of p g. Okay. And finally, we can write del E t plus 1 del W is simply, this is the error term and this is the gradient information at t plus 1, this particular term. So, now it is a very simple relationship. Okay. So, now weight update law is, this is the final weight update law. Okay. So, what you saw that in this weight update law, W t plus 1 is simply its previous weight into the error, instantaneous error t plus 1 into learning rate and gradient information at t plus 1. So, how do I compute this gradient information p w t 1? Using this recursive relationship. Okay. So, that is p w t plus 1 is computed using the gradient information that is already computed at t. So, that is p w t into g plus x t, the input at t, into this particular information, okay, term. So, similarly also p g t plus 1 is computed here, gradient information at t plus 1, second gradient information using the previous one. All right. So, how do we go about it? So, in the beginning, the first 0 instant, we assume p w 0 and p g 0 to be 0. Once we compute that, then we can easily compute what is p w 1. Once p w 1 is computed, which is p w 2, you see that if I put t equal to 0, then p w 1 is y 1 into 1 minus y 1 x t, which is x 0, plus g p w 0, and this is 0, and so on. And once I have p 1, I can compute p 2, p 2, p 3. So, this is like this. I start from p 0 and then compute p, sorry, let me not confuse you again like back propagation. I will put in terms of forward propagation. So, I have p w 0, this is 0, and from there I compute p w 1, and from there I compute p w 2, and so on. So, this is called forward propagation of gradient descent algorithm, forward propagation of a gradient descent algorithm. Okay. So, we are now ready to discuss a little more complex network, which was a very simple last one, which was a single neuron network. Now, I have 3 neurons, 1, 2, 3, and be aware how we put the network weights. You see that this is second neuron. So, the weights coming to this neuron is all initialized W 2, and from where it is coming? 2. Like this is W 2, from where it is coming? From 1. So, this is W 2 1. Similarly, this is W 2 and coming from 4, W 2 4, okay, and there is no connection between 2 and 3. Okay. That means this is a little partially connected, not fully connected. Fully connected means there should be at least a connection from here to here. Okay. So, similarly W4 is connected from 2 3, not from 1, okay, and similarly. So, these are the convention. You please see that for W43 is a connection weight to unit 4 neuron 4 from unit 3. Similarly, W34 is a connection weight from 4 to 3, and of course W33, W22, W44 they are all self feedback, they are connected self feedback, and these connections all have single delay. We assume that all these connections are single delay. Okay. So, based on that assumption we will write what is the forward response of the network. So, S2, S3, S4 are actually S2, S3 and S4, they are the total sum, input sum to the neuron 2, 3 and 4 respectively. So, S2 plus 1 is W21 X1 T plus W22 X2 T, W24 X4 T, that you can see here. So, the input to the network 2, which is I can say as 2 T plus 1, this is the input to the neuron 2 is W21 into X1 T plus W22 into X2 T plus W24 X4 T, only 3. This the total 3 input signals are there to this neuron 2. So, this is the summed input to the neuron and then sigmoidally activated. Based on that we compute what is X2 T plus 1 is f of S2 T plus 1. Okay. So, the forward response of the network is just you compute what is S2 T plus 1, S3 T plus 1, S4 T plus 1. After computing the sum, the total sum input of the total sum of the total input to the neuron, and then the final response is the sigmoidal activation of the total sum input. And finally, the response of the network, if you look at here, is Yt plus 1, which is X4 T plus 1. So, that is what we write here, Yt plus 1 is X4 T plus 1. Okay. So, this is a, and all activation functions are sigmoidal. This is all activation functions are sigmoidal f. Okay. So, derivation of the sigmoidal weight activation function. The weight update law is as usual is a gradient descent law, but now my cost function is a time function, it is a dynamic, because Et plus 1 which is Yt plus 1. So, Yt plus 1 is a function of Yt and as well as other neuronal internal states. So, that makes the difference. So, Et plus 1 is this instantaneous quadratic function, that is Wd Yd plus t plus 1 minus Yt minus plus 1 square half. So, this is again instantaneous error because this is real time recurrent learning, that is output. So, what you do is that I want to now compute Et plus 1 upon del Wjk, and what is Wjk is can be anything, because we have how many weights here. If you look at here, we have total 9 weights, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, total 9 weights are there. So, obviously, with respect to x4 or y, we have 9 gradient information at any instant. Similarly, with respect to 2 x 2, when here also there is a gradient information. So, with respect to x 2 we have total connection here is we can compute all the weights actually, because x 2 can be function of all the weights actually, because that is the that is the meaning of feedback, because x 2 t plus 1 is a function of all the weights. This is very important to understand. Okay. So, the del E t plus 1 del w j k is obviously, if I want to differentiate this one with respect to any typical weight w j k. So, we get here this particular term error, and when I differentiate this with respect to w, negative comes out, del w del y t plus 1 upon del w j k. This partial derivative will define this partial derivative. We will, instead of y, we will write x4, because that is the convention we will select, that all active neurons the output is x. So, x1, x2, x3, x4, as many neurons are there, that many that will be the subscript for the x. So, y is x4 t plus 1, and we will define this particular function as pjk4. That means the differentiation of x4 t plus 1 with respect to wjk is p4jk t plus 1, and same thing when computed at t, it will be t minus 1, it will t minus 1, but this the way to write this is p4jk. Similarly, if I want to write del, if I want to write del x3 t plus 1 by w jk will be p 3 jk t plus 1. So, this is the way we define the gradient information. As usual, we showed in the simple recurrent network with one neuron. Similarly, if you go on computing this particular thing, del y t plus 1 upon del w j k, then you will differentiate y t plus 1 with respect to s 4 t plus 1, okay, because this is a function of s 4 t plus 1. If you differentiate, and then s 4 t plus 1 with respect to w j k, if you differentiate. So, if we want to differentiate this this x4 with respect to wjk, so you can easily see that previously s4 is this particular term. So, if I differentiate del s4 t plus 1 by del wjk, so you can easily see I am differentiating this particular term with respect to del wjk. So, this is a constant term w42, and this is x2t you differentiate with respect to wjk. By definition, this is p2, 2 will come here, jk and t. The second one is w43 is a constant term again, and then x3t is differentiated. This you differentiate x3t with respect to wjk. So, again this is p jk and this is 3t plus, and again here this is a constant w44 and t, again this is with respect to 4 and jk t. Okay. So, this is what is your, by definition we are computing S4 in terms of gradient information in the previous step. So, by doing that you easily see that Pj4t plus 1 is this particular term, and the one extra term that is coming here is, if you go here, if you go here, if you imagine that if jk by chance, if it is by chance, okay, is either 42, 43 or 44. So, this is not actually complete information, I made a mistake. So, this is so WJK also, this JK can be either 42 or 43 or 44. If that is the case, then obviously if it is 42, then differentiation of this will be also x2t, simply x2t, or if it is JK is 43, then differentiation of this with respect to WJK besides this term is also x3t. So, this is what is the last term, that is delta JK is 1 if j equal to 4, okay, and then this is 1 and into xk. So, that is either x2 or x3 or x4. Okay, that completes how to compute PJK4. But we also we learnt how to compute the gradient information which is PJK4 at t plus 1 with respect to the other gradient information at t. But what about this also in this particular expression there are also gradient information PJK2t, PJK3t, PJK4t. So, PJK4t we already did that. So, we have to also find the gradient information, that is how do we relate PJK 2t plus 1 with respect to all other gradient information. So, this also we can always write, because this is simply if I go to the previous page, if I write P 2 JK t plus 1 will be f S2 t plus 1 derivative of that that is S2 x4 x2 t plus 1 into 1 minus x2 t plus 1 into, you can easily see that I have to differentiate now this particular term with respect to JK. So, it is same what we computed here, this will be simply W21 and this will be P1. You must know that x1 is an input. So, I cannot actually write this, I can't write this, because if I differentiate this with respect to WJK, x1 is an input. So, input is not a function of WJK. So, we will omit that. First we will start from here. So, that is W22 P2 JKT plus this one is W24 P4 JKT plus, as we said, this is JK XK. That is if JK is either 21 or 22 or 24, then corresponding term x1t or x2t or x4 will appear here. Okay. So, and that so this is your PJK2t plus 1 in terms of the other gradient information at t. So, similarly we can find out, as we saw, we can find out the gradient information recursive relation for PJK3, PJK4 like that. Once we do that, okay, this is what is similarly PJK3, PJK2, we did that, and then we do not have to go exclusive. This is, for example, we simply say JK. Now, instead of JK, if I write 3 1, how do I compute? So, you can easily see P4 3 1 t plus 1 is this particular thing. Now, we go to the system identification, an example. We have taken this example earlier for also in previous class. This is a linear dynamical discrete system. This is a linear discrete system. So, yt plus 1 is minus 0.5 yt minus yt minus 1 plus 0.5 ut represented by a real time recurrent network. Okay. So, yeah, how do I represent this network? We have already explained. In feed forward network, in a feed forward network, this will be yt from the system, ut, this is yt minus 1, and one more is ut. So, you have 3 input and output is yt plus 1. In contrast, the recurrent network is a memory network because it has its own internal memory, and ut is the input and yt plus 1 is the output. It is like, and it has its own internal. So, here the first one is single delay and second one is double delay. So, what does it mean? So, I can write now yt plus 1 is W3 ut plus W1 into this is single delay. So, W1 into yt single delay, and then double delay is W2 into yt minus 1. Okay. So, if I match this into this, so I can write, you can easily see yt, and this is a, because this is a linear discrete system, in this case yt plus 1 is simply W3 ut plus W1 yt plus W2 yt minus 1. This is linear. So, this network response is this. This network has this response, the linear dynamic. So, obviously, I do not know what is W3, W1, W2 of this network. What I know is that I can generate data from this particular model, mathematical model. I can use my MATLAB or C language, whatever any computing program I can use, and generate ut, which is a random number, say between 0 to 1, and then I compute what is given u0, what is y1, given u0, u1, u2, u3, u4. So, then corresponding what is y1, y2, y3, y4, y5 and so on. So, I compute this data and give those data online, that is I compute one, I give one input, find the output, give that here, match the error, back propagate, update the weight, and again generate a new data from this model, give it to the give to this network and compute what is the output, match with the actual output, and go on like that. And finally, what I should see, that W3 should be 0.5, W1 should be minus 0.5 and W2 should be minus 1. So, that should be the result. So, that is, we will see what is happening here. So, the response of the system is W1 yt plus W2 yt minus 1 plus W3 ut, where W1, W2 are unknown weights. Cost function, instantaneous cost function. So, Wit plus 1 is Wit minus, this is gradient descent rule, and as usual real time recurrent learning means we put this this is our usual error term into gradient information at t plus 1. So, we have to now compute W1 Pw1 t plus 1 in terms of the gradient information in the t. So, if you look at that, it is very simple here. If I want to differentiate this particular thing, which is Wyt plus 1 by Ww1, if you look at here, okay. So, with respect to W1, if I differentiate this one, is simply first one is with I am differentiating with respect to W1. So, W1 into if I define this is simply P W1 T plus here also if I differentiate the W1 I simply have YT. So, this if I differentiate this with respect to W1, so I get first YT and then W1 into del YT upon del W1 which is this one plus W2 is not a function of W1. So, simply W2 into P W1 T minus 1 plus here of course there will be no term because neither of these is a function of W1. So, this is your if you differentiate. So, this is actually your this with respect to W1. So, that is P W1 T plus 1. So, if I look at now this same thing YT W1 P W1 T W2 P W1 T minus 1 which we showed here. So, similarly we can find out what is P W because I have how many weights? 3 weights. So, we will have 3 gradient information P W1, P W2, P W3 right. So, after we found the arterial rule, now we will generate data. What we did is that we generated 100 data points using dynamic model. UT, this is UT was a random number between 0 to 1. So, you can easily see all these blue are the input and correspondingly the output was from minus 2 to 2.5 the output and using arterial for one sequence of time the final weights that is you have 100 data set and over that when you train finally you get after training W1 is minus 0.5, W2 is minus 1 as required and W3 is 0.5. So, what you are seeing here that in this particular network I only give recurrent network the real time my input is only UT, whereas if I would have trained the same data set I should have 3 input to the network. So, this is 3 by 1 and this is 1 by 1 network. So, this is more like a dynamic network. So, recurrent network is a dynamic network. Okay. So, RMS error versus number of epochs. Okay. So, you can easily see that how RMS error is decreasing and going towards 0 almost like number of epochs is 1500 and so you see that how the weights are evolving. So, in the beginning all the weights were initialized to be 0 here W1, W2, W3 initially W1 was 0, W2 was 0, this is initial and as training progressed the weight got settled at this weight which is W3 was settled at 0.5. So, this is 0.5 value and this is W1 which is settled as minus 0.5 and W2 which is this one is settled at minus 1 and which are desired. So, this is the error surface. If you look at the error how in the error surface the weights glided to the bottommost position the global minimum. With a linear network you always reach a global minimum using gradient descent. So, we compared this same system we trained using simple back propagation through time as well as real time recurrent learning. So, after 2000 epochs we found simple back propagation gave 0.001 RMS error, back propagation through time gave 0.005 little more, where real time recurrent learning is 0.0009. So, you see that the dynamic network does better it captures the dynamics better. So, in this lecture what we learnt is that we learnt the architecture of a recurrent network. We also presented a new training algorithm, means a training algorithm using RTRL, real time recurrent learning algorithm. This is a online learning algorithm. Also we compared, we took a simple example, and on that we compared how three different learning scheme works. So, as this is a course on intelligent control, I hope that you appreciate the system at least in the beginning. I have presented neural network as a system identification tool, because that is a better way to look at neural network models from a control perspective. Thank you very much.